Welcome to the last part of the problem-solving session for chapters 31 and 32. In fact, we don't have any questions to solve for chapter 32, so we finish up with chapter 31 questions. And question 10 is also a Lenz's law question, but we didn't want to make part 2 too long, so we're going to just begin with the last question in our grouping of Lenz's law. Here we're told that there is a magnet with a south pole that moves towards this arrangement where there is a circular loop that is connected to a rectangular loop with a resistor in between the points A and B. And we're asked to determine which of the following is true. Is the potential from B to A positive number, or is it from B to A negative number? And here's what we have to keep in mind. If VB minus VA is positive, that must mean that VB is a positive and VA is a negative, because VB will be higher than VA, and so this will result in an outcome where the difference delta V between the points B and A is a number that is positive or greater than 0. If, on the other hand, VB minus VA is negative, VB is a negative number, VA must be a positive number. So when we take negative minus positive, we end up with a negative number. So now we're going to apply Lenz's law to make a determination of which of the two applies in this case. Well, we can see that there's a south pole which is approaching this loop, and when this loop sees this, because here's the external magnetic field points out of the north, because this loop sees that the magnetic field external is increasing towards it, it tries to prevent that increase from occurring, and so it produces an induced magnetic field in the opposite direction. In other words, this would be the north of the induced, and of course that means that this is the south of the induced. Notice south to south, which obviously implies that there is a repulsion here to try to prevent this external magnet from getting any closer to the loop. Well, Chapter 30, we use the right-hand rule when we have a magnetic field in this given direction here. Use the right-hand rule, and we see that we have an induced current which is flowing in this direction here, which when we look at it from this side is the counterclockwise direction. Sorry, the induced current there. Well, that means that it's going to flow downward. It's going to flow along this side, and along this side. And the current always flows from positive to negative because there's a potential drop along the resistor. Well, the positive would be the high potential end, which is at point B. The negative is at the low potential end, which is A. And so we see that VB minus VA is in fact a positive quantity. So here, let's go ahead and circle that the right answer here is that VB minus VA is greater than 0 because we're going from high potential to low. So a bigger number minus a smaller number equals a positive number. Well, the last question here, which again is chapter 31, is a generator question. We're told that the output from a generator is shown here, the EMF, and this right here, milli, is e to the minus 3. So this is in millivolts, and time is also in milliseconds, so this is e to the minus 3. So we're given EMF as a function of time. We're told that the coil of the generator has an area of 2e to the minus 2 meters squared and has a total number of 150 turns. We're asked to determine the following quantities. The period, in other words, the time to complete one oscillation. Well, that's capital T, and we can extract that information right here from the graph, where you can see that the wave takes 2 seconds to be fully completed. I'm sorry, 2 milliseconds. Let's not forget that. So T is equal to 2e to the minus 3 seconds. Part B asks us to determine the frequency of the generator. Well, the frequency will be 1 over the period. So here, let's just add some units to make this more relevant to us. 2 milliseconds per cycle, and the frequency will be 1 over 2e to the minus 3 seconds per cycle, which gives a number of 500, and this time it's cycles per second. See, it's the inverse of t. We then are asked to determine the angular speed of rotation of the coil, that's omega, and we can calculate omega by taking 2 pi times the frequency, and that takes us 2 pi times 500, so we can write this as 1,000 pi radians per second, or more specifically, if we want a number, we get 3,142 radians per second. In part D, we're asked to determine the maximum EMF, and the way we determine that is by looking at the graph right here. See the amplitude? It's the magnitude of the amplitude is 5 millivolts, so the maximum EMF, which is the amplitude, is 5e to the minus 3 volts. And then lastly, we're asked to determine the magnetic field of this generator. And to get B, we simply note that the maximum EMF will be related to N, B, A, omega, because remember that the EMF as a function of time is E max times the sine of omega t, where E max is given by NBA omega. And please recall that the NBA omega the B and the A came from the magnetic flux, which was constant. The N comes from Faraday's law, so let's just write this down here as a reminder. So minus N times the change in the magnetic flux with respect to time. And the magnetic flux, the B and the A, does not change, but the change is coming from the derivative of cosine of omega t with respect to t. And of course, the derivative of the cosine of omega t is minus omega sine of omega t. Well, this minus cancels that minus sign, and if we put everything together, you can see we've got the positive here, N, B, A, omega, right there, and then sine of omega t. So this sine of omega t is from here. So going back to getting the magnetic field can be obtained as E max divided by N A omega. See, from this expression right here, N A omega. Well, E max we saw was 5e to the minus 3 volts. N we are given, sort of running out of room here, as 150 turns. A was given to us as 2e to the minus 2 meters, and that was already squared for us. The omega, which we calculated, was 3,142 radians per second. When we multiply it all out, we get a value of B, which is 5.31 e to the minus 7 Tesla. Well, this concludes the last part of the problem-solving session for the unit covering chapters 31 and 32. Until next time.